Welcome to this explainer. Today, we're taking on a really exciting core mission, which is translating the everyday world around us right into the syntax of Java object-oriented programming. Now, if you've ever felt like computer science concepts are just this bunch of abstract, floating ideas that don't really connect to anything real, I have great news for you. By the end of our time together, you'll see that everything in Java fundamentally mirrors the logic of the actual physical world. Okay, let's dive right into this. So here's our mental roadmap for the explainer today. We'll kick things off with real-world objects, then we'll move into classes as blueprints, talk about hiding complexity, look at working with methods, and finally wrap the whole thing up with Java data types. All right, part one, real-world objects, how we perceive our world. Okay, so in Java, an object is a logical entity, but it actively represents a real-life entity. And it's defined by three absolutely crucial characteristics: state, behavior, and identity. Now, what about identity? Well, as a user, you actually don't usually see this part. It's an internal mechanism entirely for the JVM, the Java virtual machine, to distinguish one specific object from another. Basically, it's their unique fingerprint hidden inside the system. To make state and behavior a bit more tangible, let's just use a classic example. Picture a bicycle. The state represents the object's data or value at any given moment. So for our bike, its state might be that it's currently stationary or maybe it's moving. The behavior, on the other hand, represents the operations it can perform, like the actual working of the object. For the bicycle, this is applying the brakes or pushing the pedals. In Java, an object completely encapsulates both its specific state and its behaviors right inside itself. Now, here is the crucial point of confusion we need to clear up right away: the difference between a class and an object. Think of a class as the abstract blueprint. For example, a car. The concept of a car applies to literally any brand, any make, any model. But an object, that's the specific real entity that actually rolls off the assembly line. A Maruti car is an object. It represents one single, physical, touchable entity, whereas the class car represents the entire overarching idea of those objects. Moving on to part two, classes, the ultimate blueprints, manufacturing those blueprints. When we build a Java class, it starts with the keyword class, followed by whatever you want to name it. And inside those curly braces, which is the body of the class, we have two main things: data members and member methods. The variables, like int a and int b, act as the object's state. They store the raw data. Then, the member methods, like a sum function, act as its behavior. This blueprint encapsulates literally everything the object knows and everything it can do, all neatly packaged in one place. While we're on the topic of variables, there's an incredibly important distinction in how the computer handles memory. We have instance variables and we have class variables. An instance variable means every single time you create a new object, a new instance, it gets its very own totally unique copy of that variable. But if you use the static keyword, you create a class variable. This means the variable is created exactly once in memory and is then shared among all the objects of that class. It basically belongs to the blueprint itself, not the individual objects. Let's jump into part three, hiding the complexity. This is all about security and usability. To really wrap our heads around this, I want you to think about this question for a second. How does an ATM really work? When you put your card in, the machine authenticates you, it checks your PIN, pings the bank server, verifies your balance, physically dispenses cash, and updates your account. But as a user, you don't do a single bit of that math or networking. You just push a few buttons on a screen. That ATM experience, it perfectly defines our next core concept: abstraction. Abstraction is the act of showing only the simpler, relevant details to the user, while keeping all the complex, unnecessary inner workings entirely hidden. Just like you don't need to understand the complex electronic wiring of an ATM or a calculator to use them, Java classes use abstraction so that you can interact with complex objects without needing to understand the hundreds of lines of code making them run. It's what makes programs actually usable for humans. But if abstraction is about usability, encapsulation is all about security. Encapsulation is defined as wrapping up data into a single, secure unit. It enforces a strict barrier that completely prevents the outside world from directly accessing or messing with sensitive data. I mean, you definitely don't want just any random part of a program accidentally overwriting your bank balance variable, right? Encapsulation hides that data, ensuring it can only be accessed by the specific trusted member functions of that class. And how exactly do we build those protective barriers in Java? We use access specifiers to control data visibility. Private means the data is only accessible within the class itself. That's your maximum security setting. Public means it's wide open, accessible from anywhere. Default restricts it to just the same package, and protected allows specific subclasses to peek in. By carefully choosing the right access specifier, programmers basically play traffic cop, tightly controlling the flow of data.
All right, part 4, working with methods and objects. Time to actually execute some code.
So creating an object from a class can look like totally intimidating syntax at first glance, but it's really just a simple, logical 1, 2, 3 checklist. First up is declaration. You just declare an object name and link it to the class data type. Second is instantiation. This is where that magic new keyword comes in, actively allocating real physical space in the computer's heap memory to hold this new object. And third is initialization, calling the constructor to give the object its initial state right out of the gate. Once that object is alive and breathing in memory, how do we use it? The secret is the dot operator. By typing the object's reference name, followed by a simple period, a dot, you unlock access to its internal state and behaviors. Typing something like a.p accesses a piece of data, while typing a.sum1235 actively triggers one of its methods. The dot is literally your bridge directly into the object. Let's deconstruct the methods themselves for a second. A method is completely useless until it's called, but to build one, you really need to know its anatomy. The method prototype is that entire first line you write. It includes the access modifier, the return type, the name, and the parameters. The compiler reads this to understand exactly what the method is going to do. The method signature, however, is slightly different. It's just the name of the method and the data types of its arguments. And remember, when you finally call a method into action, you can either call by value, which means sending a copy, or call by reference. I want to quickly clear up two closely related terms that trip up a ton of beginners, especially when reading error messages or taking a test. Formal parameters are those placeholder variables you write when you are actively defining the method in your class. Actual parameters are the real, concrete values you pass in when you call the method to execute. So formal is the setup, actual is the real-time execution. Okay, our final section, part 5, Java data types, the raw data categories. At the very, very bottom of the Java universe are the primitive data types. Think of these as the absolute atomic building blocks of all information in the language. There are exactly 8 of them: int, byte, double, char, short, boolean, float, and long. They contain pure, simple forms of a single kind of data. But precisely because they are so simple, there are major limits to what you can actually do with them. Which brings us to a massively important comparison. The alternative to a primitive type is a composite data type. So what's the big difference? Well, when you perform an operation on a primitive, you are working on a copy of the original data. If you pass it to a method, the method just gets a photocopy. But with a composite data type, you are working with a direct reference to the original data. If a method changes a composite data type that you passed as an argument, it alters the original source forever. Honestly, keeping that distinction in mind will save you hours of debugging later on. And this brilliant little revelation brings our entire explainer totally full circle. Because what exactly is a composite data type? Well, arrays are one example, but the primary example of a composite data type is a class. That's right, the class, the blueprint we spent this whole session learning to design, encapsulate, and abstract, is ultimately just a complex, custom data type that we built ourselves to hold a specific set of primitive values and methods under one easy-to-use name. It's all connected. So, as we wrap up, I want to leave you with a quick challenge to cement all of this in your mind. Look around your room right now. Pick 3 physical objects. If you had to code them in Java, what would be the broad class for each? What variables would make up their state? And what methods would define their behavior? If you actively apply this technical vocabulary to your immediate everyday surroundings, you will never forget it. Thank you so much for joining me for this explainer. Keep exploring the code around you, and I will catch you next time.